Now I want to solve this nonlinear partial differential equation of the first order written like this. ut, which is the partial derivative of the function u with respect to time, is equal to x times the derivative with respect to x of the function u minus u. So the function u is a function which depends on the two variables x and t. And we can see that x belongs to the real axis, t is greater than or equal to 0, and f of x, which is this function here, this is the initial condition, because we set t equal to 0, we can see that this function is infinitely many times differentiable. And another assumption is that we have to assume that f is equal to 0 for the absolute value of x greater than or equal to 1. We have to solve this problem by using the method of characteristics that I will introduce and discuss the behavior of the solution. Okay, we have to solve this equation anyway, this equation right here. And we are going to do so by supposing that the variables x and t depend on a parameter. This is the method of characteristics. We are going to assume that u can be written like this. U of x of s, this is a parameter that I have introduced. T of s, I have introduced the parameter s. It's as if the points xt belong to a curve. This means that u is also a function of s, and therefore we can consider the derivative of u with respect to s, the total derivative. And this is equal to u sub x, so it's the derivative of u with respect to x times dx over ds. This is the chain rule, plus u sub t dt over ds. Now let's rewrite this equation like this. This is simply u sub t dt over ds plus u sub x dx over ds minus du over ds equal to 0. Let's also rewrite the equation that we have to solve. The equation that we have to solve can be written like this: u sub t minus x times u sub x plus u equal to 0. Now, take a look at these two equations here and compare them. If we compare these two equations, we can see that if we set dt over ds equal to 1, this one here should be equal to 1 because here we have just u sub t. So if we set this equal to 1, we get exactly u sub t, which multiplies 1. Because here we have 1 times u sub t. Something similar for this factor here. So we set dx over ds. In this case, this is equal to minus x, as you can see here, because we have minus x, which multiplies u sub x. And then we set minus du over ds equal to u, because these two here must be equal if we want to solve exactly this starting equation here. So let's try to solve these three equations. They are very easy to solve actually. By solving these equations, we will be able to solve the starting equation. If we solve this one, we have t equal to s plus some constant that I will call c sub 1. If we solve this one, we are going to get, this is a very easy differential equation. We get x equal to e to the minus s times some constant that I will call c2. Whereas if we solve this one, we get u equal to e to the minus s times c3. Now we can choose an origin for the parameter s. And in particular, we can choose s such that at s equal to 0, we get t equal to 0. This is just a choice, which means that c1 is equal to 0. And therefore, t is equal to s. Now this means that u of x of s, t of s, is equal to e to the minus t times c3, which we see from here. But now we have to try to find out more about this c3 and about this equation up here. x equal to e to the minus s times c2. So let's find out. In particular, let's set s equal to 0. If we set s equal to 0, we get u of x of 0, t of 0, but remember that when s is equal to 0, we choose t equal to 0, so here we get 0. And this is simply equal to c3, because e to the minus t when t is equal to 0 is 1. But what is c3? Well, we can find it also from this condition. Let me enlarge it. This condition here, u of x0 is equal to f of x. So this means that c3 is equal to f of x0. But what is x of 0? X of 0 is equal to c2. You can see it from this condition, because if s is equal to 0, we get x equal to c2. So this is f of c2, which means that c3 is a function of c2. And let's do one more step. From this equation here, let me do it in red because this is important. We can also rewrite c2 as x times e to the s. And also remember that s is equal to t, so this is equal to x times e to the t. So now we have to be more general and rewrite this as f of x times e to the t, which means that we can rewrite u of xt in terms of the two variables x and t instead of the variable s. This is simply e to the minus t, as you can see from here, which multiplies f of x e to the t. And this is the solution to the PDE, partial differential equation, that we started with, which also complies with the boundary conditions. Let's also take a look at the behavior of this function as t goes to infinity. Well, as t goes to infinity, this exponential will decay very fast. Therefore, u of xt will go to 0. And also remember that the function f, not u, but the function f, is equal to 0 for the magnitude of x greater than or equal to 1, which means that we should consider this magnitude here, the magnitude of x e to the t, greater than or equal to 1. This will imply that u will be equal to 0, because f is 0. So we can also rewrite this, for example, as mod x greater than or equal to e to the minus t. And that's it for this problem.